All right. So look, what Casey didn't tell you is that this project that I'm going to talk to you about is the funnest thing I've done in like the last 15 years, and it is super clearly the midlife crisis that I am enduring. Okay. Um, the origin of this was, Peter Van Dockum came to Toronto to be the external examiner for one of my graduate students. And we went out for beers after the exam. And hey, thank you. Is that mine? Thanks a lot. So what happened is we spent 2 hours complaining. Okay, so Peter at the time was chairman of the astronomy department at Yale. I was, on the board of Gemini. I was our graduate chair. Was just about to become president of the Canadian Astronomical Society. It was just terrible. Okay, and we spent 2 hours just complaining about how our lives had just taken this downward trajectory and nothing was fun anymore. And in particular, the planning for large instruments was sucking up our lives. And that was the suckiest part of the whole enterprise. And we were like, where's all the fun? We used to be having so much more fun. When we were grad students, it was super fun. When we were postdocs, it was super fun. Supposedly, we're successful, and now it's just sucking. And so at that point, Toronto had just been given its largest private donation ever. So in Canada, we're a bunch of socialists, so people don't tend to give universities money for things other than hospitals. Through a curious series of events, we got $130 million to found this thing called the Dunlap Institute for Astrophysics. If you've not heard about it and you're working in astronomy, Google it. It's amazing. Okay, and one of the least sucky admin things I was engaged in at the time was coming up with a white paper that defined what this thing was going to do. And so one of the things I thought that this thing should do is it should be kind of like a startup factory for astrophysics, so that what we would do is we would come up with, we would use this cash, the interest of which we could spend forever, okay, to test the thesis that in astronomy, we're still working in a model where the universe is so completely unexplored, it's easy to envision graduate student type innovative projects, Silicon Valley style, where you can do something fast and make a mark. So you don't have to embark on this, $15 million, 10-year Gemini instrument. It's possible to be physicists like most of you, okay, and still do small-scale, impactful projects. And so this whole endeavor, okay, is midlife crisis intended to demonstrate it's still possible to do astrophysics in that mode. And so that's what Dragonfly is all about, okay? And so what do you do, I guess is the question, okay? It sounds good to say you've got a ton of cash and you can do whatever you want, but what do you do that's impactful and that you can do fast, okay? And so the answer in astronomy, I think, is you look in an unexplored area of astrophysics, because that's the story, okay, of our subject. Whenever anybody has figured out a technology or other way of looking in some area of the sky, in some bit of parameter space nobody's ever looked at, some wavelength nobody's ever looked at, the universe has rewarded him or her with amazing discoveries. So that's the thing that kind of inspired us, okay? We're just going to look in some region of parameter space that nobody's ever looked at before. And Peter and I both, I guess, are old enough that, this was the textbook, when I was in grad school. So when I started grad school, this guy here was our, your president. I said our president, not my president. Okay, your president in Oxford. And I turned up in Oxford, and I was like the most horrific ignoramus. Because I had done an undergraduate degree in laser physics, and here I was. I wanted to do astronomy, but I was in the UK, where they have a 3-year PhD program, and there is zero coursework. Okay, so what do? So I panicked, and day one, I went to the bookstore, and I bought this book, and I read it cover to cover. Okay, so in this book, there was this plot, which I couldn't get out of my head. Okay, and so what this plot showed was that if you plot, and it is cutting off the top of it. Never mind. Okay, so what this shows is the luminosity of galaxies. Okay, so this is a very faint galaxy. This is a very bright galaxy. So luminosity is increasing this axis in dumb astronomer magnitude units. Okay, and this is the size of a galaxy, and so this is in kiloparsecs. And so what you see is that all galaxies known at that time, so this is 1988, 89, I guess, existed in this band, right? And so why is that? There was no astrophysical reason for it. So the most likely thing is that it's a selection effect, okay? So things that exist up here are likely to be confused, okay? They're probably there, but they're classified as stars. They look stellar. So down here, there's likely to be a ton of objects, but their surface brightnesses are too low. So hands up everybody who knows what the surface brightness is, because radiometry is a bit fussy. So less than half of you. So I will explain it. Okay, so I've got a laser pointer, and look at that bright red dot. Okay, easy to see. So imagine that I put a lens or something ahead of this, okay, so that I diffuse the light, and so it's spread over a much bigger area. So it'd probably be a lot harder to find. Okay, so that's the fundamental idea, okay, is you've got the energy, but the detectability is a function of not just the energy being emitted, but how that energy is distributed over an area. Okay, so if I have and this is a simulation, okay, so in my simulation, I have this circle, and it's got 1,000 stars. If I then, and it's on a noisy background, right? Easy to see. If I make that circle bigger, and I conserve the number of stars, the amount of energy, spread it out over a bigger and bigger area, it becomes harder and harder to detect. Okay, so that's the idea, okay, is that, the galaxies that we're familiar with are probably, existing in some surface brightness regime. The amount of light per unit area is up there, easy to find, but nature may have lots of things that are at low surface brightness, same amount of energy over a much bigger area, and we're just not finding them. So that's the thing. In 1989, that was the context. The more modern context is totally different, okay, and there are people here working on this, so I presume many of you know that in the local universe, if galaxies are constructed in the way that we think they're constructed, in this paradigm of hierarchical galaxy formation of dark matter halos, which have lots of other satellite halos, because you build big galaxies by the coalescence of little galaxies. Something like the Milky Way should not just have a small number of dark matter halos, it should have many thousands of them. So where are they? Okay, so if you plot, again, these are dumb astronomer units, so this is bright and that is faint, and this is distance from the Milky Way. If you plot the local dwarf galaxy population on this diagram, you get these red points, okay? And what you see is that, there aren't, many thousands of things here. There are just a few tens of them here, okay? So this is, in principle, a problem if you say that every dark matter halo has associated with it a bunch of stars. People will argue about that, but that's, in principle, at least a huge problem. Okay, so this is called the missing satellite problem, and we're building bigger and bigger things to try and dig into this bit of parameter space to see whether or not we can find more dwarf galaxies. So there's interesting work being done here with instruments to try and find them, and we are succeeding in finding them. So if you then take this and you cast it into the sort of framework I was describing in the previous plot, using surface brightness as the thing to think about, what you see is luminosity along this axis and size along this axis, and this magic line here corresponding to 30th magnitude per square arc second, right here, and there's nothing at lower surface brightness than 30th magnitude per square arc second. So I'm using two dumb astronomer units for that, okay? Magnitude and arc second squared. But this is actually an important number to remember, okay? 30th magnitude per square arc second represents the Rubicon, okay, that nobody has really managed to cross in taking a direct picture of something. That's the surface brightness below which we can't cross just by taking a picture. Now, you can get to lower surface brightnesses by resolving galaxies into individual stars and then bidding up and playing games. But if you just want to take a picture of something, you can't get below 30th magnitude per square arc second. So what's interesting is that it is 2018, and we were stuck at 30th magnitude per square arc second since 1974. Okay, so in the intervening period of time, our ability to detect fainter and fainter galaxies has increased by a factor of almost 1,000. It's more like 850, depending on what you allow me to take as a detection with the Hubble Space Telescope is. But we can go like 1,000 times deeper, okay, in terms of finding fainter and fainter galaxies in the intervening, like, 50-ish years, and yet we've not been able to figure out how to get to lower surface brightness. So there are two questions you should be asking yourself. Okay, firstly, why is this so hard? And secondly, why should I even care? Okay, so let's take the first one second and the second one first. Why should you even care? That for some reason or another, we are evidently too stupid to figure out how to get below 30th magnitude per square arc second. So the reason you should care is because there's a treasure trove of known astrophysical phenomena that exist below this threshold. So if you could get below this threshold, you would likely find, okay, just a debauch of little missing satellite galaxies that would be of direct relevance to this missing satellite problem. You'd be able to explore the galactic outskirts. So galaxies right now are thought, when you look at a picture of a Hubble picture of a galaxy or a picture taken with a local telescope, you see that galaxy with your visible wavelength eyes. But if you had radio eyes, that galaxy should be twice as big. Okay, so the lore is that at radio wavelengths, galaxies are twice as big because you're seeing this neutral gas, which extends way further out than the starlight. And at its maximal extent, that gas should be connecting with this thing called the cosmic web, which is these filaments of dark matter that unite all galaxies and that is sending material in to build up the galaxy. So that should be visible at ultra-low surface brightnesses. If you don't care about galaxies, if you just care about the solar system, did you know that somebody detected a new ring around Saturn, discovered it in 2015, okay? This was discovered with the Spitzer Space Telescope and glowing dust radiation, but every major planet in the solar system should have comparable dust rings, right? Just waiting to be discovered. Supernova light echoes. So at the lowest surface brightness levels, space becomes dynamic. Okay, so we're used to taking pictures of things and thinking, oh, well, that's looking the same way now as it'll look in 100 years. But there are these things called supernova light echoes that are the relics of light from historical supernovae that are moving across the sky, moving degrees per year. So if you could get down to low enough surface brightness levels, the universe would open up and look much more dynamic. So you could actually look at the radiation from the historical supernova that in 1054 blew up, was detected by Chinese astronomers, resulted in the Crab Nebula. You could see it. Nobody knows what type of supernova that is. You can take a spectrum of it, okay, if you can get to low surface brightness. There's a whole host of other things that I don't have time to talk about. Okay, so you should care. Okay, so assuming now that you do care, what's the problem? Why can't we do this? Why in the last 50 years have we figured out how to make these better telescopes that have allowed us to detect galaxies 1,000 times fainter? And yet, what's stopping us from getting to lower surface brightness? So the problem is systematic errors. That's why I feel good talking to physicists, because you guys understand this. Astronomers, as a rule, don't. Okay, because we live in this world where if we want to see something further out, we build a bigger telescope, right? That's their cure. You just get more photons. But there's a class of problems, kind of an edge case, okay? But there's a class of problems for which the bigger telescope does not provide the cure, because what's limiting you is not the number of photons you collect, but it's the systematic errors. This is an example of that. Okay, so the floor here is systematics. So the sucky news, the bad news, okay, is that the systematic errors that limit you are also the systematic errors that make it possible to build the large telescopes that we've been building for the last 100 years. Okay, so the systematic errors include things like using reflective surfaces. Okay, so 100 years ago, state of the art was the giant refractor. Since then, we figured out that it's 99% of the time much smarter to build a large reflecting telescope. But the aluminized coating that allows the large reflector to exist is a source of scattered light that ultimately limits your ability to go to low surface brightness. Another thing is an obstructed pupil. You have a big mirror, and then you have an obstruction because you have a secondary mirror that focuses the light onto your instrument. That obstruction is also a source of scattered light. So what am I saying? Am I saying that if you want to get to low surface brightnesses, we have to go back to this era? So you might recognize this person. No, I'm not saying that at all. So to be even more emphatic, no. Okay, so that would be stupid. Okay, and so the reason why that would be stupid is because what are you optimizing for when you build a bigger and bigger telescope? Okay, so you've got Darren's right there. So he'll tell you that the figure of merit depends on whether or not what you're trying to do is to detect the faintest possible star over a small area or the faintest possible star over a large area. So let's say you're trying to detect the faintest possible star over a small area using adaptive optics. Your figure of merit then goes as the diameter of your mirror to the 4th power, right? So in that case, clearly the thing you want is the biggest freaking telescope you can get your hands on. Okay, d to the 4th. That's called the d to the 4th advantage of adaptive optics. Let's say there's an alternative. Okay, the alternative is, I don't necessarily want to have the sharpest image, but I want to, take advantage of the best image quality delivered by Earth's atmosphere, but over a big area. Okay, so the figure of merit there is d squared times the field of view of your telescope divided by the seeing or the image quality squared. Anyway, the point there is it's d squared. Okay, so your figure of merit there goes as your aperture squared. So also, your smart move is to make a bigger telescope. Okay, so in the first case, I'm basically describing adaptive optics with, say, for the next generation telescopes, like a 30-meter telescope design. In the second case, I'm talking about a telescope that to 0th order is the GMT design, or even the LSST design. Okay, so both of those are what you want 99% of the time. One of those two. Okay, but there's a edge case, the third case, and the third case is where you don't care about the resolution of your telescope at all. The only thing you care about is whether or not you can get to low surface brightness. So in that case, your figure of merit is this. Okay, so this is actually the focal ratio of your telescope, the speed of your telescope. If you go to the camera store and you buy a lens, it's an f2.0 or an f4.0. So that's the focal ratio. When you buy your camera lens, you don't ask for a particular aperture, right? You ask for a particular focal ratio. So there, in the edge case, the thing you want, okay, is not necessarily a big telescope, but what you want is a fast telescope. Okay, so the faster your telescope, the greater your ability to detect low surface brightness structures, if you don't care about resolution. Okay, so I'm not trying to detect stars, I'm trying to detect huge extended structures. So while the refracting telescope has been dead to astronomy for 100 years, the thing I showed you was the Yerkes 40-inch, still the world's largest refractor, built in 1895. Refracting telescopes have not been dead, just gotten a different name. Okay, we've called them telephoto lenses. So this is the king. Okay, so this is the Canon 400 millimeter f2.8 IS 2L. Okay, so that's a $15,000 telephoto lens. So if what you're trying to do is to take a picture of Barack Obama, your former president, on vacation in Hawaii, okay, this is your instrument of choice. I obviously would not do this with your president. In any case, so there's a problem though, right? Which is if you actually look, so this is a hyper secret design, okay? But if you're desperate enough, you can go to the Japanese patent office and get the design for the previous generation of this lens. This is what it looks like. You see that it's obviously extraordinarily complicated, right? So in particular, count the number of air glass surfaces in this thing. So that's terrible, right? Because each one of these is a source of internal reflections, because of course we're all familiar with what it would look like if you take a telephoto lens and take a picture near the sun. You would see this stuff, right? So this is these are internal reflections, and these internal reflections are a natural byproduct of having very complicated optics. So welcome to the future. Okay, so the physicists know, and astronomers didn't know, okay, that we're living in this kind of revolutionary era of optical coatings being way better than the magnesium fluoride coatings we are familiar with. Okay, so these are electron microscope pictures of optical coatings, but what? They don't look like optical coatings. In fact, what they look like are a series of cones, okay? And so they're dielectric cones laid on an optical surface. So these are called nanostructure coatings. I had never heard of them, but they are pretty revolutionary, okay? So if you coat an optical glass with a nanostructure coating, the reflectance goes from, say, So this is reflectance as a function of angle of incidence. So it goes from, say, 0.5% to essentially 0 for, even pretty oblique angles of incidence. So what does that mean? Well, basically it means that if you coat a highly curved surface, this is with the world's finest ordinary multi-reflection coating. This is with a nanostructure coating. It's perfect. Okay, so what are the implications? So let's say it's only like 99% perfect with the old coatings, okay? But you have like 15 air glass surfaces. So that means that the transmission through this thing is like 0.99 times 0.99 times 0.99, 15 times. So it means that you're transmitting like, so let's say 85% of the light. So that 15% of the light that isn't getting transmitted is getting scattered, okay? So if, on the other hand, it's 0.999 times 0.999 times 0.999, 15 times, basically it's still damn close to 0.99. So in principle, these are wonderful. So these are now commercially available. So this happy person works for the Canon Corporation, and he's got a dumb grin on his face because he's holding the king. Okay, so this new generation of lens with these new coatings became available about 5 years ago. And this is Peter Van Dockum, and he's got a dumb grin on his face. Whoa, it's not showing. There he is. Okay, so Peter, at this beery conversation, said, I bet these new 12K lenses with special coatings would be really good for astronomy. And so I said, at this beery conversation, yeah, right. It's pathetic, because I knew he was really into lenses. It's pathetic how you Canon fanboys believe everything you read. Put your money where your mouth is, smart guy. And so at this beery conversation, we did. Okay, so we thus embarked on Dragonfly. This is the origin story. This is the true origin story for Dragonfly. Okay, so it's now a collaboration between Toronto, Yale, and Harvard, but it started at this beery conversation over a bet, where Peter bet that these lenses would be terrific for astronomy, and I bet that they would not. And so we each bought half a lens. So this is why it's good to be old, because you have discretionary funds that you can do this kind of stuff with. Okay, so this is co-owned by Toronto and Harvard. So this is a CCD camera I got from our undergraduate lab. This is Yale's undergraduate lab equatorial mount. This is a guide scope I scavenged from my backyard. So this is at the Observatoire du Mont Mégantic in Quebec, which was equally inconvenient to get to from Toronto and New Haven. So we met there with these various bits, assembled a telescope, and we started taking pictures of things, and I lost the bet. Peter was right, okay? So this is the wide-angle point spread function of Dragonfly. These are on scales of a degree or so. So this is the Dragonfly point spread function, and this is, all manner of other telescopes. So this is actually from a paper put together by somebody who didn't believe we were right, and independently analyzed all of our data and this other data himself, and published it. So on large scales of like a degree or so, Dragonfly is, and again, stupid astronomer units, like 2 magnitudes better than any other thing on the planet. So, okay, so let's start doing some challenging math. Okay, so 3 is better than 1. 8 is better than 3. 10 is better than 8. 24 is better than 10. And 48 is better than 24. Okay? And the reason it's better is because of this. Okay, so effectively, you can, so that's cut off, but that's square root of n times d. So the effective aperture of a Mosaic telescope like this is the square root of the number of little telescopes multiplied by the aperture of an individual telescope. So individually, each Dragonfly lens is a 6-inch telescope. So the square root of n, where n is 48, gives you an effective aperture now of 1 meter. So that's not an accident. Dragonfly now, because we now have 48 lenses, is the world's largest all-refracting telescope, bigger than Yerkes by like a nanometer, but still. Okay, but the real thing that matters is the effective focal ratio. Okay, so the effective focal ratio is the focal ratio of an individual lens divided by the square root of the number of lenses. Okay, so effectively, Dragonfly is operating like an f0.39 refractor, okay, which is actually faster than the thermodynamic limit. So the second law of thermodynamics says you can't have an optical system faster than f0.5 unless you cheat like this, in which case, that's what you get. So you can have a 500 lens dragonfly, and that would be a 3-meter aperture at 0.12 refractor. And that's actually not crazy. Like, we're seriously thinking about doing that. Because the cost scaling is so great. Okay, so dragonfly goes with effective aperture grows as d squared, whereas a conventional telescope, it's more like d to the 2.5, and the enclosure goes as d cubed. So you can make a dragonfly surprisingly cheap, surprisingly easily. And if you do, and you start taking pictures of things, you actually have to be cunning, because if you just point dragonfly at the galactic North Pole, where you'd think you'd see nothing but extragalactic things, instead this is what you see. Okay, so this is called Galactic Cirrus. So I was barely aware of the existence of this stuff, because ordinarily you don't see it on astronomy pictures. Okay, but actually this stuff it's vermin everywhere. You know. Unless you avoid Galactic Cirrus, with Dragonfly you go to such low surface brightnesses so fast, this stuff is everywhere. And so now that's the new systematic. Okay, so Galactic Cirrus are basically infalling clouds of gas and dust infalling into the galaxy from outside. So if you care about Galactic Cirrus, Dragonfly is the ultimate machine for it. But if you don't care about Galactic Cirrus and you're interested in studying stuff in between it, that's what you got to do. So everything I'm going to show from now on was carefully chosen to only look in patches of the sky where we pre-identified on the basis of IRAS, this infrared astronomy satellite images, that they were in holes in the Galactic Cirrus, because otherwise, that's all you see. So it's cool. It's a cool concept, though. Okay, so this is showing the Dragonfly field of view. This is going to be the field of view of the Large Synoptic Survey Telescope. So with the Large Synoptic Survey Telescope, whose field of view is kind of comparable to Dragonfly, it's like Darren, what does it cost? It's like $700 million? Yeah, it's $700 million, because you have a huge telescope and your focal plane is enormous, and so you have to have a mosaic of lots of little CCDs. What we're doing with Dragonfly is we have a mosaic of lots of little telescopes. So it's kind of a mental jujitsu way of looking at the problem. But the field of view you finally wind up with is kind of comparable, even though the aperture of the LSST is much larger, but Dragonfly is much faster. So there are different areas of astrophysics where Dragonfly is actually superb. And I have like 20 minutes to try and talk about them, okay? So these are various things that we have done and that we want to do with Dragonfly, and I'll talk about as many of them as I can squeeze into the next 20 minutes. But this is what very familiar galaxy M101 looks like. We took a picture with Dragonfly, and the thing is, since this is exploring such a open area of parameter space, you point Dragonfly at almost anything and you discover something. So for this, we discovered a very extended disk that is much larger than had been known, and we discovered 7 candidate dwarf galaxies, 4 of which turned out to be bona fide new dwarfs for M101. This is like one of the most famous galaxies known. People have been taking pictures of it for 120 years. So point at anything and you'll find something new. So what do you point at? Okay, so the first thing we did was we probed stellar halos. So this is really why we built Dragonfly. Okay, so the idea is that in this hierarchical picture, you build up big galaxies by smashing together little galaxies. So imagine what would happen if you took a car and you smashed it into another car. Okay, so you would have a couple of crumpled cars, but you'd also have bumpers and rear view mirrors, all of which are have flown off hundreds of yards, right? So the idea is that the signature of this picture of merging big things through the coalescence of little things happens at high energy, and some of that material winds up incredibly far out. So that's what we thought and still think is one of the few truly acid tests of this basic picture. All galaxies should have at low surface brightnesses a very, very extended, 5 times bigger than anything you see with a conventional telescope, debris field of low surface brightness stellar structure. And the question is, do you see it? Okay, so we conducted a modest survey. Alison Merritt, who sadly has been truncated, led this. So here's an example. Okay, so this is the Sloan imagery for these galaxies in the interior. And in some cases, indeed, you see it, right? So in other cases, however, you do not. And that, in fact, is the message, right? So unlike the prediction, which is that every galaxy should have an extended stellar halo, the reality is that nature is building up galaxies evidently in a much more diverse way than anticipated. So this shows the mass of the galaxies in our sample. The red galaxies are shown here. This is a numerical prediction for what might be expected. Here's another family of predictions. This is the fraction of stellar mass in the halo. And what you can see is, here are a bunch of galaxies that evidently fall, well in agreement with the prediction. But what about these? Nature has somehow figured out a way to build big, massive galaxies without an extended stellar halo. Yeah. Yeah. Mm-hmm. Yeah, so that's at least in the Aquarius simulations, they're in there. Yeah, so all the components are reflected in these simulations. So, truthfully though, of course, we all know the shiftiness of the theoretical astrophysics community. And so even though this, felt like a ironclad prediction that would actually be something falsifiable, it took weeks before people could come up with, so for example, you can have a geometry where you have the satellites only coming in along the same axis as the disk of the galaxy. So it builds that way, but it builds a big disk and it doesn't build a big stellar halo. So there are edge cases to the numerical simulations that can explain this stuff now. Anyway, okay, so look, so we did this, so 2 idiots and 2 non-idiot grad students did this. We did it, from a standing start in like 2 years. Meanwhile, there's a beautiful, actually, HST program, our $6 billion space telescope also sort of did it. Took much longer, though. So this is called GHOSTS, and it's actually an excellent program. So what they did was they used what I mentioned earlier, which is you can also get to low surface brightness if you can resolve galaxies into individual stars. And then you're not limited by the systematics I've just described. Okay, so you can also do it, with little pencil beams with Hubble. And so GHOSTS, so this is the plot I showed earlier. So this is stellar halo mass fraction, and this is the mass of the galaxy. So this came out after us. So you can see our dragonfly points shown in gray, and this is what you get with Hubble. So it's broadly consistent, okay? So you can get at this problem 2 ways, either by resolving the individual stars, or you can just have a bunch of idiots taking pictures of things. And so I think it's encouraging, that you can do this in these 2 different ways. So the implications are that you need to build galaxies in more complicated ways than the standard model. Right. So another thing you can do, I mentioned earlier that if you have radioized regular galaxies are twice as big as if you just have, visible wavelength eyes. So we tested that. So this is NGC 2841. So this is the radio view of this galaxy. This is the visible wavelength view. And once again, I need to make it dark. So what you can see is that we have starlight extended to the limits of the radio data. Okay, so if you're sensitive enough to low surface brightnesses, then dragonfly, wherever there's gas, neutral gas, there's stars. And that should be impossible, okay? So stars should form in molecular clouds, so molecular hydrogen, not neutral hydrogen. And so that's why we thought for a long time that you shouldn't have stars out as far as you can see the radio data, because you can't form stars in that environment. So I don't know why, but you can, okay? So if you look at the mass surface density in stars, which is shown in blue here, and then the mass surface density in radio, H1, so this is neutral hydrogen, then you take the ratio of it. So this is out about 70 kiloparsecs, okay? And this is about almost 30 scale lengths. So galaxies have their light dropping off exponentially, right? And so this is 30 scale lengths. So this is like e to the minus 30, which is obviously a pretty freaking tiny number of the central light density. So this is really faint, okay? There's a constant ratio. So the visible portion of the galaxy with conventional imagery goes out to about here. So when you do that, it looks like it's dropping off exponentially. And, it is, but it continues out really, really far. And for some reason, there's a constant ratio, okay, of mass in starlight to neutral gas. And I don't understand that at all. Now, one possible way is if you could form somehow stars in the neutral gas, then however much amount of neutral gas you got, you should also have a bunch of stars. I have no idea. An alternative is that if you're forming stars in the neutral gas in the cosmic web, and then that material sails in to build up the galaxies, then somehow you could also wind up with this constant ratio. I offer no hypothesis. I don't understand it at all. Okay, so that's a second cool thing we found. Let me tell you about a third cool thing we found. So the two things I've described so far were the product of disciplined scholarship, okay? But we are undisciplined people, okay? And so we could not resist pointing Dragonfly at, what should be the best studied area of the sky, called the Coma Cluster. People have been pointing telescopes at the Coma Cluster again for like 100 years, okay? And so the Coma Cluster is, an immensely massive, relatively nearby, extraordinarily well-studied portion of the sky, and we just couldn't find it in ourselves not to point Dragonfly at it, okay? Because it is in a hole of Galactic Cirrus. So we did, okay? And so this was not part of anybody's PhD program. We just did it for the hell of it. And it's so far led to the most impactful Dragonfly results. So maybe there's some sort of moral lesson there. Okay, so the thing that jumped out instantly is that we took, one picture of the Coma Cluster, and we started seeing that there's just a huge number. We found 50, but there are now hundreds known, of these things that have now come to be known as ultra-diffuse galaxies. So this is a Dragonfly G plus R band image of one of these things, and this is a CFHT I band image. To just make the basic point, because when I give these Dragonfly talks, people tend to be overly enthusiastic, which is good because they obviously like Dragonfly, but I don't want to mislead you. Okay, look how much more obvious the ultra-diffuse galaxies are than the CFHT image, but look how terrible Dragonfly is for finding compact things like background galaxies and stars. 99% of the time, you want to find these things. But if you're interested in finding these things, Dragonfly just knocks the hell out of CFHT, okay, which is purported to be one of the world's finest wide field imaging telescopes. So build the instrument appropriate to the science that you wish to do. Okay, so what do these things look like? Well, ultra-diffuse galaxies, which were in nobody's models, okay, turn out to be about as big as the Milky Way, but have 1/100th to 1/1000th of the stellar mass. So the reason this is so surprising, okay, is because, in a numerical simulation, the way you sort of, the numerical simulation is dominated by dark matter, but you don't see the dark matter, you see the stars. So to translate the numerical simulation into predictions, you map from the dark matter to the stars by using roughly a fixed ratio, okay, of stars to dark matter. This is called abundance matching. What this is saying is that abundance matching is wrong, okay? To 0th order, it's wrong anyway. So these things are, if they're massive, as suggested by their sizes, and that's a big if, okay, if they're as massive as suggested by their sizes, then somehow nature has contrived a way to build galaxies with hardly any stars and tons of dark matter. So since we found ultra-diffuse galaxies, this field has basically exploded, with much of the work being done by theorists trying to explain why these things have existed. So there are now like 700 papers on ultra-diffuse galaxies. But largely speaking, okay, you can just say that the models fall into two families, that of failed giants or inflated dwarfs. Okay, so a failed giant would be, you have a massive dark matter halo, which for some reason has failed to make stars. The alternative is you have a small dwarf galaxy that for some reason or another has just been stretched out and become much bigger. So there are ways to do that. For example, you could imagine angular momentum doing it. Okay, if you have a dwarf galaxy that for some reason is just spinning much more quickly than expected, then what you would get would be a much larger galaxy, but you've just spread out both the dark matter and the stars. So which of these two options is true? Which of these is what nature is doing? So this is where the Coma ultra-diffuse galaxies live. So this is size in kiloparsecs. This is surface brightness in dumb astronomer units. So these are, this is the whole of the Sloan survey. These are these local dwarf galaxies at very low surface brightness that you can get at because they're so near you can resolve them. And this is where ultra-diffuse galaxies lie. And the point I'm trying to make here is that this is a bona fide new population. So are they inflated dwarfs or are they failed giants? Okay, so I don't know, but I'll tell you, I think they're a mixed bag. And so let me give you some suggestion for why this might be. So this is Keck Spectroscopy. Okay, so this is not easy to do. So I find hilarious that you can discover these things with the telephoto lens, and to follow them up to learn what's going on requires 20 hours of integration with the world's largest telescope. Okay, but this is what a 20-hour Keck spectrum of one of these things looks like. It's got a velocity dispersion, telling you how fast the stars are moving, which is telling you how massive it is, of about 50 kilometers a second. So this is clearly a pretty massive one. This one looks pretty similar. Okay, another ultra-diffuse galaxy in Coma, but its velocity dispersion is 40% of that one. So the mass is lower. So these are tricky observations to interpret, though. Okay, because you're actually only measuring the velocity dispersion in the central part of the galaxy, and you have to extrapolate it out to large radius in order to get the total mass. So extrapolations are large, and that always makes people uncomfortable. So in principle, there's a better way to do this, and we were too stupid to figure out what that was. We relied on other people to tell us what that might be. But I'm showing you this picture, and if you look at this picture of the ultra-diffuse galaxy, Dragonfly 44, so this is what conventional galaxies look like. That's what Dragonfly 44 looks like. And if you look at this and you go, gee, I wonder what these little dots are, then you are smarter than Peter and Bob, or at least smarter than me. I don't want to speak for Peter. Okay? So what those things are globular clusters. And so other people figured out that because other people work on globular clusters. Peter and I are high redshift people, but people that work on dwarf galaxies and globular clusters pointed out that there is this relationship. So this is the latest manifestation of this relationship by Mike Hudson and collaborators between the number of globular clusters in a system and the mass of that system, the total mass, including dark matter. So this is Bell Harris, I think, probably deserves the majority of the credit for this. But anyway, what this is you count the number of globular clusters in a thing, and then you go down here, and that is the mass of that thing, including all of the dark matter. So in principle, that's a better way to go, because the globular clusters extend much further out in the galaxy than just the central bit that you can get a spectrum of, even with 20 hours using Keck. So here's the picture. This is taken with Gemini. So Gemini is a telescope which I have been involved in for a long time, and there's good and bad aspects of it, but man, sometimes when it is good, it is so good. So this is a 0.3 arc second seeing from the ground image of a, so the astronomer should have a sharp intake of breath, and the physicists are like, whatever. But that is exquisite, within a factor of 3 of HST from the ground. So these are globular clusters that we have modeled. This is a luminosity function that we fitted to these things. We've counted these things up, and we've worked out that the stellar mass of this thing is entirely comparable to that of the Milky Way. Okay, so this object, Dragonfly 44, is a failed giant. So what this is basically a naked dark matter halo with a tiny patina of stars, 1/100th to 1/1000th of the stellar content. Okay, so just to get this out of the way, who knew that when we were doing this stuff, it would be of interest to people studying dark matter? But apparently it is. Okay, because it turns out that objects like Dragonfly 44 are, you can model them as being the perfect laboratories for trying to understand the nature of the dark matter particles. So this is a paper by, Ostraker, Tremaine, and Witten, and presumably their postdoc that they were working with, who probably did 80% of the work. So this is a fantastic laboratory for testing things, but we're not going to let those theorists have all the fun. And in particular, we're going to hold their feet to the fire with actual predictions. Astronomers, this is a big deal for us, actually making people predict stuff. Physicists do this all the time. We can learn from them, okay? So here's a prediction. So this is Carlos Frank. This was at the Galapagos Islands meeting like 10 months ago. And so this is a prediction for the number of dark halos. So this is the, so this is the fraction of galaxies that should have dark halos as a function of stellar mass. And the important point is that Dragonfly 44 is over there on this. It's actually off this scale, and it's 0. Okay, so there's nothing in this simulation that looks like Dragonfly 44 by like 2 orders of magnitude. So Carlos, whom I love, is shifty, and so I bet you he'll come up with a way of having those things appear. But to 0th order they are not in anybody's simulation. So, okay, you guys like question time, right? So I will, let me blast past a lot of my remaining stuff. To conclude quickly with this. Okay, so where are we gonna, so we built this thing, what do we do now? So we can go from n equals 48 to n equals 500, that's one option. And we're seriously considering that option. But okay, what this says is that this is Greece's greatest philosopher, so that's Socrates, or Socrates, if you, Bill and Ted's Excellent Adventure is a movie for some of us. Okay, so that's Greece's greatest philosopher. Let me show you Canada's greatest philosopher. So this is Wayne Gretzky, okay, who said, "I skate to where the puck is going to be, not to where it has been." And of course, that was famously stolen by Steve Jobs, introducing the iPhone. And so we're trying to skate to where the puck is going to be. So where's the puck going to be? I think the puck is moving from individual galaxies to the intergalactic medium, because if you look at a n-body hydrodynamical simulation, so this is a 10 megaparsec cube for the non-astronomers here. 1 megaparsec is the distance to the Andromeda galaxy. 20 megaparsecs is the distance to the Virgo cluster, which is the nearest big cluster. So this is a huge honking chunk of the universe, okay? And so when you look at this with dark matter eyes, what you see is dark matter halos everywhere, and they're connected by these filaments, this filamentary structure known as the cosmic web. But when you use your eyes and you look at starlight, because that's what we do, all we see is this. Okay, so now the interesting thing is that the dark matter filaments are not devoid of baryons. Okay, what they're devoid of is stars. So they have gas. It's just incredibly tenuous, but it's also photoluminescent. So if you look at the distribution of photoluminescence from the gas in the dark matter halos, that's what you would get. Okay, so in principle, if you, and this is insanely low surface brightness. So if someone were able to come up with a wide field, ultra low surface brightness mapper that could look at the photoluminescence from a hydrogen line over a big area, you'd actually be able to tell whether the universe looked like a dark matter simulation. Gee, I wonder how you could do that. So one way you could do that is by putting a big, so each of these filters is about $15,000, but you could put a big ultra narrow band hydrogen alpha filter ahead of every one of these Dragonfly lenses. And if you were able to do such a thing, simulations suggest that over integration times of thousands of hours, so this would be hard, you would be able to directly map at least the brighter portions of the cosmic web and start directly seeing the distribution of the largest collapsed structure in the universe, the cosmic web. And so this is work that we're currently embarking on. It's completely nascent. In fact, we pushed the button on the filter order the day before yesterday. Okay, so I don't know where we're going to be, but I will tell you that before we embarked on this crazy project just a few years ago, this was the world's largest refracting telescope, and this is it today. Okay, and that was Dragonfly with 24 lenses. It's now at 48, so that's what it says, 48. And what it should also say is for now, because we're not sure where we're going to stop, except I will stop here. Okay, thank you. Sure. Yeah. Right. Listen, I think that is the most intelligent question anybody could ask following my talk. So thank you. If you hadn't thought of that one before walking into this room and you did it on the fly, I salute you. I totally agree that that is the most important thing we can try and figure out is how do we calibrate this relation? It's a completely new class of objects. So with your indulgence, because I want to end on time, I feel otherwise it's unprofessional. Let me show you one thing. Okay, so this is a secret in that it's coming out in Nature in the middle of the month. Yeah, so no freaking social media. I'm serious, actually, because they can pull the plug on the paper. Okay, so this is the nearest ultra diffuse galaxy, but it's not in Coma. Okay, so this is around a galaxy NGC 1050. Can we make it dark again? Because otherwise all these are always mega lame. So if you look at NGC 1050, like I told you, point Dragonfly anything, you'll find something new. So one thing that was found that was new was an ultra diffuse galaxy. Okay, so this object, so Coma is 100 megaparsecs away. This thing is 20. Okay, so it's not as big as, or likely as massive as the Coma UDGs, but this one's super near, so we can do stuff like resolve it into stars. So Peter, I was going to say we, but it was Peter's Keck time. So it's Peter, used Keck to take spectra of these, what we figured would be globular cluster candidates. And so here's what we got. Okay, so these are, a calcium triplet, lines, which we were able to well fit using Charlie Conroy's models. And if we look at the systemic velocity of those globular cluster candidates, here's what we get. Okay, so this is the distribution. So this is the systemic velocity of the galaxy, and this is what we would predict just on the basis of, nothing other than that, the standard mass to light ratio. We would expect a velocity dispersion of 32 kilometers a second, which is this dotted red histogram. This is what we actually find. Okay, which is basically no motion at all. So anyway, the Nature article will be called "A Galaxy with No Dark Matter." So it's just crazy. Okay, we've got ultra diffuse galaxies spanning the range from 99% dark matter with Dragonfly 44 to 0% dark matter in this thing. So I don't know what's going on. One alternative is that we're just seeing this thing, although it looked like an elliptical galaxy, we're assuming it's 3D. It's not. It's a disk that is just seen face on, and that's why we're not seeing any motion. I don't know. But, the simplest interpretation is that nature has just chosen to make galaxies with an incredible variety of the mixing between dark matter and baryons, far larger than we thought. And so in some cases, they appear to have hardly any dark matter. In other cases, they appear to be almost completely dark matter dominated. And the reason we didn't know that is because we just hadn't known about ultra diffuse galaxies. So anyway, that's a interpretation. Whether or not it's right, I don't know. Yeah, okay, so that is what, the answer to your question is, let me punt. In some cases, we for sure see things that are better interpreted, in my opinion, as a thick disk than a stellar halo, just because they don't get rounder. You just stretch the image like crazy, and you see it gets fatter, but it doesn't explode into like a spherical stellar halo. But we have not done a systematic test. The one galaxy in our sample that we described, that I have just described, was like at a 60-degree angle. And the reason was because we were really, really paranoid when we were doing this experiment to only point in regions where there was hardly any galactic cirrus, because we just didn't figure we could handle any galactic cirrus. But now we're like, we think we can tell the difference between galactic cirrus, which is striated, and something that's round like a stellar halo. So we're now going back and doing, and this is my student Colleen Gilhully's PhD. We're going back, and Colleen has defined a sample of 35 edge-on galaxies at a range of stellar masses, and we're going to go and try and work that out. And so the goal here is, so we've just made a fantastic hire in Toronto, Joe Bovey, who says that our perception or our view of how we build up stellar disks is naive, and we should be thinking about building up stellar disks as a kind of a layer cake, where the closer you are to the disk, the younger you are. And so what we expect to see in this case is, rather than having a thick disk, it should be a series of disks of various ages. And so it would be great to see whether or not we could detect such a thing with Dragonfly. So stand by. I don't think it'll take long. Now that Dragonfly is 50 lenses, we could replicate Allison's survey, which took 2 years. We can do it in maybe a couple of months. So I think that Colleen will have her thesis dated by the end of this end of this year. Sure. So this, no. Yeah, okay, so another thing. I'm sorry, this is my sneaky way to show all my slides. So this is, So I think it might have nothing to do with environment. Okay, so this is the um, HST Frontier Field Observation of Abell 2744. So these are some ultra diffuse galaxies my student Steve Jansen's found. Okay, so if you then plot the number of ultra diffuse galaxies as a function of um, the, the virial mass of the structure, you go from wimpy groups all the way to the most massive galaxy known. So this is actually from Steve's paper. He's just updated it, included all of the frontier fields, and they're all up here. There's just a straight line, and the slope of the straight line is consistent with unity. Okay, so I think what this is just saying is that, you take an ice cream scoop of the universe and you just count the number of galaxies. For every massive galaxy, there's a fraction of UDGs, and the environment doesn't seem to much matter. Yeah, yeah. Well, I just showed you one. Sort of. Not. Yeah, it was associated with NGC 1052, I guess, but it's not in a cluster. Yeah. Yeah, we didn't. Yeah, but it's not. We didn't point at voids and look for ultra diffuses. Yeah, I don't know. I think we should actually. The thing I found with Dragonfly, and this is the joy of this thing, is every time I think I know what's going on, it turns out that it's 180 degrees opposite. So if there should be no ultra diffuse galaxies and voids, we should look in voids and probably find a bunch. Yeah. 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 Yeah, so there's this trait. I'm giving most of the credit for the success of these particular lenses to the coatings, but I think that's actually unfair because only a couple of elements are coated, and maybe even just one. It's a secret. Okay, and so I actually think it's also way easier to just baffle the hell out of a telephoto lens, so you get no scattered light from anything else. So I think it's a combination and then it's all refractive. So I think it's lots of little things that kind of come together. But then the interesting question becomes, what starts limiting you? Because I haven't shown you here, but we're now embarking on, deep observations to try and figure out what our limiting systematic is. Because we're going to hit it, we just haven't hit it yet. And so I think what it is confusion. Because we have these 2.8 arc-second pixels. And so when you start going really, really deep, the background starts getting kind of naughty. And what's happening is you're just seeing all of this unresolved structure. But the reason we picked these particular lenses is because with the 6-inch aperture, the diffraction limit is, well, it depends on the wavelength, obviously, but it's like 0.8 arc seconds, which is better than our sight. So what that means is that all I require in order to continue to succeed and get higher and higher resolution is for Moore's law to make the sensors in these things better. Because we have these 5-micron pixels on our CCDs, but this has a 1.2 micron pixel. So if I could just figure out a way to get the sensor from this thing behind Dragonfly, I'd have a 4 times higher resolution. And so that's where we're going. We're also experimenting with whether or not we can get CMOS sensors, essentially cell phone sensors, and stick them on the back of this thing, have higher resolution, and then I think confusion won't be our limiting factor. So anyway, so that's why I think you should, really, really little apertures. I think maybe not the way to go, even though you get these huge fields of view, because your diffraction limit then is several arc seconds, and there's no way, there's no cure. It's just nothing you can do about it. Mhm. Yeah, yeah. I think that'd be an awesome idea. Yeah, yeah, yeah. Yeah. Well, your f1.8, 20-degree field of view lenses are not diffraction limited. They're good, but so that the amazing thing about these lenses is I couldn't believe it. But I did a Rodier test on these things. and the Estrella is like 0.8, which is just barely diffraction limited, but it's amazingly good for a, it's this long. So Canon knows what they're doing, but so do astronomers, And there's a lot of stuff in these expensive lenses that we don't use. Like it has an image stabilization unit that actually was screwing us up. So we had to tape it up. Like we actually sent it to Canon's headquarters in Costa Mesa and got them to actually put adhesive over this thing to stop it from moving. Yeah. So we turned it off, but it had a element that would shift around. Yeah. When you, yeah. Yeah. Well, no, I haven't. I'm a little scared, but anyway. Okay. Right. Yeah. So yeah, sadly I don't have the slide here, but if you go to Zhang, Abraham et al., my grad student Jayli Zhang just published a paper showing. Well, actually, I showed you some data, but not the picture. So if you look at NGC 2841, what you see is that the disk seems to sort of flare out when you get to like 60 or 70 kiloparsecs, which we're interpreting as a warp as the disk reaches. Essentially, it's beginning to reach a radius sufficient that it's beginning to communicate with the cosmic web. So there's a postdoc, Ria Silva, who who claims that she can explain these enormous disks by having. I mentioned the preferential alignment with these locally. Satellites are not distributed randomly throughout the local universe. They're arranged in these sorts of sheets. So if you imagine you're embedding a big disk and it just happens to be aligned with the geometry of that sheet, and so the satellites would come in also preferentially aligned with the disk, then what they would do is just basically add angular momentum and energy to the disk and make it much bigger, but they wouldn't puff up into a stellar halo. But the signature of that, because it's very unlikely that it would be perfectly aligned, is that you get a warp. And so that's what we're interpreting this thing as. The disk is that enormous because it just has this preferential alignment with the local, infalling sheet of satellites, and the warp we're seeing is basically the signature of the disk talking to the large-scale structure. So how cool is that? Basically, you're reaching the limits of the galaxy itself and seeing the interface between the galaxy and the larger universe. So anyway, so that's the signature of the instability that I think you're talking about, and we might have detected. We could be wrong, and it could just be warp for some other reason.